science. And today it is my great pleasure to introduce Dr. Thomas Serre. Dr. Serre is an associate professor in cognitive, linguistic, and psychological sciences at Brown University. He did his PhD in computational neuroscience at MIT with Tommy Poggio, working a lot on HMAX and similar models. And he did his pre-PhD studies in France. His research focuses on understanding the neural mechanisms that underlie the recognition of objects and complex scenes. And to do that, he uses behavioral imaging and physiological techniques. And these experiments he uses to inform the modeling that he does, and with the goal of creating models that not only help explain human visual processing, but also are as good at humans at doing whatever they're being built to do. He's the recipient of the NSF Early Career Award and a Darby Young Faculty Award. His research has been featured in the media several times, including on the BBC series Visions in the Future, and has appeared in numerous news articles. So please join me in giving a warm welcome to Dr. Serre.
Do I need the... Oh, it sounds pretty loud, no? Can you guys hear me fine without the microphone? Perfect. Thank you, Chris. Thank you very much for the kind invitation. I had a wonderful time yesterday at dinner, and throughout the day, I think we have a wonderful department and group of faculty here. Truly interdisciplinary, and I think, well, I enjoyed it very much, so thank you. All right, so just to get a sense, do I have mostly engineers in the room? Who are engineers? Okay, and who are more psychologists, neuroscientists? So it's mostly engineers. Okay, so I'll try to combine, ideas from, neuroscience, psychology, and kind of engineering, computer vision. So I might forget to define some terms. By all means, please raise your hand and ask me to define or clarify whatever it is that I forgot to mention. I have a tendency to either dwell too much on some slides and have a lot to cover up towards the end. So I'm perfectly comfortable going through only a quarter of my talk if need be. So please ask questions, interrupt, and that will be great. Before I start, let me acknowledge the people who actually did the hard work. So Sven Eberhardt was a postdoc in the lab who actually just left for working on Alexa at Amazon, and Drew Lindsley is current postdoc in the lab, and then I have two amazing graduate students, John Kim and Matt Ritchie, that have done a lot of the work that I'm going to be talking about today. All right, so let me start by a little demo. So I'm going to show you what I think is by far my favorite psychophysics task. So I'm going to show you an example on the left here of what is called a rapid visual categorization task. So here I'm going to be flashing images. Some of these images will contain animals, some will not. Here's I think it's connected online, so that might be a bit slow. But you get the idea. Images are flashed. Of course, in the lab, this would be flashed much faster, about 50 millisecond image presentation, and then we would give subjects anywhere between 500 milliseconds up to a second. And those tasks have been extensively used to emphasize how uniquely fast and accurate our visual system is. For psychophysicists, this has been a great tool to study what the visual system can do and cannot do when pushed to its limit. Here, the limit being processing time available. So this has been extensively studied in human primates, but luckily for us, we're not. This capability is not uniquely human. Our close cousin, primates, are perfectly able to solve these tasks. So here's an example that I'm going to show you of the result of a collaboration with people at CNRS in France who have been able to train monkeys to solve very similar tasks. What I'm going to show you here is actually a real, you're going to see a live version of the task, where here to actually further constrain visual processing, not only is the image presented fast, but there's going to be what we call an eraser mask immediately following the stimulus. So the eraser mask is essentially noise, and the goal of the mask is essentially to flush any kind of remaining activity following the presentation of the mask. So here we go. So here the monkey is doing an animal task, and it's so fast that you don't even see the stimulus. And you see this is an example of a go-no-go task where here the monkey is holding a button and touching the screen whenever it sees an animal and holding on the lever otherwise. So what is interesting as a side note about monkey, we were talking about it over dinner yesterday. Monkey are not only as accurate as human, and we've made a side-by-side comparison, but they are actually faster, about 50% faster, presumably because their brain is smaller and allowing them faster conduction times. Now, just because two visual systems, human and monkeys, have the same level of accuracy during the same task, does not necessarily mean that they share the same visual strategy. Right? So to calibrate and assess how much of the visual strategy used by monkeys versus humans, we actually did a simple, we performed a simple measure where we looked at a large database of images that we presented to humans and monkeys, and for each individual image, we look at the fraction of subjects that were correct or incorrect on this particular image. So we get a score from 0 to 100. 0 means everyone was wrong, 100 everyone was correct. And then for monkeys, averaging out over many trials, we can get a similar score. And what is pretty obvious here from this plot, I'm not going to get into the detail, but what you can already see from this plot is that the correlation between the two species, the pattern of correct and incorrect responses between the two species is highly significant. Okay? And this is published. If you're interested in the detail, you can check out the paper. But the point that I'm trying to make here, by way of introduction, is that when you speed the visual system, you could expect people, subjects, to start making random errors due to just simply speeding up their motor system. Here we find that there's a significant pattern of correlation in terms of correct and incorrect responses, both within species but also across the two species. And the point that I'm trying to make here is that from this pattern of correct and incorrect responses, there is a lot of useful information that we computational neuroscientists can exploit in terms of trying to essentially reverse engineer whatever visual strategy and whatever visual representation they are relying on to solve this problem. So in fact, over the past couple of decades, we've learned a great deal about presumably the computations underlying this ability to rapidly categorize and recognize objects. So what I'm showing you here is a monkey brain, a side view of a monkey brain. This particular set of areas here correspond to the ventral stream of the visual cortex, which is a set of areas that are thought of as playing a key role in our ability to process shape information and object recognition. So the stream starts at the back of your head here in the primary visual cortex. And then the visual signal undergoes a series of transformation whereby it's passed from one area essentially to the next. So from the primary visual cortex, also known as the striate cortex, onto extrastriate areas B2 and B4, all the way to higher visual areas, IT here standing for inferotemporal cortex. Okay? So I already alluded to a visual hierarchical organization. And this hierarchical organization is pretty clear when you perform electrophysiology on mammalian brain. First of all, if you stick your electrodes in different parts of this ventral stream, you find that the latency of the visual signal following a stimulus presentation increases in higher and higher visual areas. So just, the signal needs more time to propagate. There's also a very clear pattern so from the anatomical perspective, you find that the pattern of connectivity between those areas reflect what we understand about hierarchies at the anatomical level. And furthermore, and probably more interestingly, there's a very clear functional hierarchical organization. So if you stick an electrode in earlier visual areas, you're going to find that neurons tend to have relatively small receptive field sizes, something like a degree of visual angle or less. So I'm assuming that I guess I'm talking to imaging scientists, so you guys probably know about degrees of visual angle, but the rule of thumb is that my thumb width at an arm length distance is about 1 degree of visual angle. So we're talking about neurons performing very localized processing. And if you probe at the response of these neurons, you find that in general their preferred stimulus is relatively simple. They might be tuned to maybe things like bars and gratings at different orientations, things like different spatial frequencies. As one goes into higher and higher visual areas, one finds an interesting transformation happening to the visual representations. First of all, neuroscientists have found that the preferred stimulus of neurons across the ventral visual hierarchy increases. So you might start from things like bars and gratings detectors, and as you go in higher and higher visual areas, one finds neurons that's starting to respond to more complex stuff, which is often hard to describe in words, but people think of things like parts of objects. And then by the time you reach higher visual areas, one can find neurons that are even sometimes tuned to entire objects for those classes of objects that are ecologically important, things like faces, body parts, and depending on the species, many other things. So as we go along the ventral stream, one finds a gradual increase in the complexity of the visual representation, and in parallel to this gradual increase in the complexity of the visual representation comes a gradual increase in the invariance properties of neurons. So starting from very small receptive field, I mentioned a degree or less earlier, as one goes along this ventral visual hierarchy, one finds neurons that whose receptive fields get larger and larger. Okay? In parallel to this receptive field size increase, the neurons exhibits higher invariance with respect to 2D transformations. Namely, they become invariant to the exact position of the preferred stimulus within their receptive field, and sometimes also exhibit some invariance to scale. Okay? Now, in terms of the computations underlying this, visual transformations from input to pretty close to output, well, the past, I would say, 40, 50 years of research, starting with Yuval and Wiesel, has suggested that the visual architecture, hierarchical architecture of the kind shown here on the bottom, could provide a decent model of what's going on. Okay, so what I'm showing here is a particular illustration of the so-called feed-forward hierarchical models of visual processing. The idea is that by considering different processing stages, whereby units at one stage would receive convergent inputs from units at the previous stage, people have shown that it's possible to explain this gradual increase in both the complexity and the invariance properties of neurons as one goes higher and higher in the processing stream. Okay? One of the key predictions from this class of model, and I mentioned that they started with Yuval and Wiesel in the late 50s, and then there was many people that have done work that I'm not going to be able to attribute properly, but things, people like Perret and Oram, Edmund Rolls in England, Riesenhuber and Poggio at MIT, and many others, have shown that it's possible to replicate the tuning properties of cells in different parts of this ventral stream by considering properly parameterized classes of model of the kind that I just alluded to. One thing that I forgot to mention, which is key for the remaining of this talk, when you look at the pattern of connections between all these areas, you find evidence for both connections going bottom up, or from lower visual areas onto higher visual areas. Now, sometimes refer to this as a feed-forward connectivity or bottom-up connectivity. But there are also connections feeding back from higher visual areas onto lower visual areas, and I'll refer to this connectivity as feedback recurrent connectivity often. However, and that's the critical piece, there is a growing body of evidence, including some of the work we've done in collaboration with our monkey electrophysiologist collaborators, is that during this rapid visual processing, when the time available for responses, when we push people with fast presentations and rapid behavioral responses, the assumption is that this feedback here doesn't play any critical role. Okay? In that sense, a feed-forward hierarchical architecture, the assumption is that a feed-forward hierarchical architecture should be able to provide a good model of what's happening during this rapid visual categorization tasks. Okay? Unlike more general tasks, when people are free to move their eyes, or when more time is available for responses, whereby we would expect that feedback starts to play a key role. So one prediction made by this class of model is that in order to achieve this fit to neural data, one needs essentially to assume only two functional classes of cells, which were called, after Yuval and Wiesel, simple and complex units or cells. Basic idea behind the simple cells, I'm sure everyone here, most people are familiar with deep learning, so it's not going to come as a surprise. The basic idea behind the simple units is that they should be implementing some kind of template matching or filtering operation. Okay? The assumption is that if you pull in the right way, a couple of input units. So here, just for illustration, say units with different orientation. Via feed-forward pooling mechanisms, one can get at the next stage something selective for for a feature that's more complex than any of the inputs. Something like maybe a T-junction detector. Okay. The second class of cells needed is our so-called complex units. And so the idea behind the complex units is that they are in charge of building some invariants. And the way that can be done, and there's partial neuroscience support for this claim, is that one can consider a set of afferent units, maybe retinotopically organized, say within a neighborhood of the cortex. And by considering units with the same preferred selectivity, note that all these units now are tuned to the same preferred stimulus, T-junction, but maybe at slightly different position or scale, one can build at the next stage, via these pooling mechanisms, a unit that's also tuned to this T-junction detector, but is now much more robust with respect to 2D transformations. Okay? And the basic idea in this feed-forward hierarchical model, which are all familiar through CNNs, is that essentially you alternate between pooling and template matching and invariance pooling, template matching and invariance pooling. Okay? And so if you do that enough, one can build an increasingly complex and invariant representation within a couple of processing stages. So one of the main contributions during my PhD thesis was literally to take one of those feed-forward hierarchical models to constrain, what I would call the hyperparameters. So essentially, the number of layers, the tuning properties of units in different stages, their range of their tuning bandwidth, so on and so forth, to the best we could given the state of the knowledge in neuroscience, and then show that if we build in a model of this part of the visual system and approximate only a single feed-forward sweep through this system, we were able to replicate human behavior during one of these speeded, rapid animal and animal categorization tasks. So I'm not going to get into the detail. The point that I'm trying to make is that, circa 2007, everyone was happy. We had models that seemed to be consistent with what we understand about the anatomy and the physiology of the visual system, and ultimately that could reproduce human behavior.
Good question.
Yeah.
What do you mean by performance? Our ability to recognize the item?
Yeah, so this is a detection task, right? So people have to press either one of two keys depending on whether they saw an animal or not. So think of that binary classification. All right, but so as I said, this was about 10 years ago, and as we're all aware, things have changed quite a bit in the area of AI and computer vision. So we're now at the level where we have computer vision systems, including deep neural networks, deep convolutional neural networks, which, as I mentioned earlier, are very close cousins to these earlier models of biology. But the accuracy exhibited and the performance exhibited by this novel system is order of magnitude, I would say, better compared to what we had 10 years ago. So here I just put a few examples, but we now have models that are starting to compete with human accuracy on databases of thousands different natural object categories. We have computer vision systems which arguably can go way beyond what our own visual system would allow us to do, with an ability to discriminate, I think, above 90% for over 1 million human faces, literally taken in the wild. So to be honest, I think this is a huge achievement. I always give I tell my students, I would be surprised if anyone can claim that 10 years ago they had seen that coming. Back when I was a graduate student, I think most people were treating computer vision as an academic exercise, and I think this is way beyond what anyone would have predicted. Again, what's interesting is that it's not like we have changed our approach to vision completely, right? As I said earlier, these more modern, recent versions of deep convolutional neural networks are closely related to these earlier models of biology. So in particular, they use the same key pooling operations that actually were motivated by neuroscience facts. I mentioned simple and complex cells. I would say there are two key distinctions between the state-of-the-art today in computer vision and these earlier models. One, and probably the main one, is that learning is fully supervised. So 15 years ago, biologists or neuroscientists didn't dare thinking that an architecture that rely on so much supervision could be biologically plausible. And so the focus was on very simple learning rules for visual representations, things like ABM learning and close cousins of avian learning. So the level of supervision that's used in modern system, it relies on supervised teaching signals. So those architecture learns visual representation that are optimized for a task, as opposed to being optimized to, say, optimally encode the input signal as in a supervised learning system would. So that's one difference. The other difference that I mentioned, that I spent a good chunk of my life constraining one of those convolutional neural networks so that the parameters of the network would be constrained by biological data. Okay? Again, trying to constrain the range of receptor field sizes, the range of invariances, things of that sort. Now those architectures are optimized for performance, whether it's through explicit optimization or what we often refer to as crowdsourcing, via several iterations of the main computer vision conferences, where we have armies of students these days, many of you in the audience, that are at every computer vision conference tweaking a little bit the parameters to crank up some of the accuracy. So I guess we are working as a collective evolutionary signal in some sense. All right, but and that's probably the part that's the most hurting for me, is that despite the fact that those architecture are optimized for the task, they do not care about what some of my colleagues would call biological details. Nevertheless, they have been shown in the past couple of years that if you try to use these visual representations to fit to actual neural data, so playing the game, treating neurons as a black box, where you're given a set of images and you have to predict the outputs, and you use the visual representations derived from this deep learning architecture, optimized on more or less random computer vision databases, those newer models do better than the earlier biologically inspired model of biology. And that to me is heartbreaking, but that's a reality. All right, so what I'm going to try to do during the time that I have is, I think I share a lot of the excitement that many of us have in deep learning. What I'm going to try to do during the rest of this talk is, plant the seeds of what I think are possible areas where human vision has somewhat diverged from modern kind of deep learning and computer vision. Okay, so I'll try to make 3 points, and I'll give you, I guess, a preview of these 3 points. The first one is that I'll try to show you that the depths of processing achieved by modern computer vision and deep learning architecture exceeds that of human observers, at least during the speeded, rapid categorization task. The second point that I'm going to try to make is that if we probe the visual representations that are used by those modern deep learning architecture, again, through backprop, through optimization, through millions or tens of millions of images from thousands of object categories, there is a significant qualitative distinction between those visual representations that are deemed important by those computer vision systems and those used by human observers. So that's the second point that I'll try to make. And the third point that I'll try to make is that, I guess my first 2 points are, possible ways to improve the match between deep networks and human vision. The third point, I think, is a killer. I'll show you that no matter how hard you try, there are visual tasks that I would deem visual reasoning tasks that a deep convolutional neural network cannot solve at all. Or it can solve it through a very brute force and very impractical way. Okay, and so I'll try to cast, and I'll try to make a point that we need more than those 2 key operations, template matching and invariance pooling, and we need to restart thinking a little bit and incorporate knowledge from neuroscience, think about notions of working memory and attention. Okay, so that's my goal for the remaining 45 minutes. No, how much? 30-ish minutes, so I better get going. All right, so first I want to tell you something about processing depths, and I'm going to maybe speed up a little bit because I'm going to be running out of time. I get this plot which is far from perfect, but it's supposed to show you the trend of what has been happening in the area of computer vision. So back in 2010, so what you see here, it's what I think is counterintuitive, is that time goes from right to left here. So we have accuracy, error rate here on the ImageNet classification top 5 error, so standard computer vision data set, 1,000 object categories. Best accuracy in 2010, 28% error. Systems were shallow, 2 levels of processing. You see the trend going a little bit up, error going down. Circa 2012, this is when the first kind of what people refer to as the deep learning breakthrough. AlexNet was published, it had 8 layers, and suddenly the error rate got cut by almost half. Okay, so that was a huge improvement. As a side note, the models of biology that I alluded to earlier are somewhere in between. They have, depending about 6 to 8 layers of visual processing. So they are, more or less comparable to an AlexNet. But see what happens then. 2013, 8, then 19, then 22, and then, by now we have, residual networks which have, over hundreds of layers of processing. So from our perspective, given that, if you remember the beginning of my talk, 10 years ago, we had a model that had, just the right amount of layers, at least from the anatomical perspective, and seemed to be sufficient to account for human behavioral decisions during rapid categorization. We wanted to ask, what's happening today with those much deeper and much more accurate deep learning architecture. So what I'm going to show you next is a series of experiments. I think I'm going to skip through many of the details, but the basics is that we took a bunch of representative deep networks, VGG 16, 19, AlexNet, and then we attempted to train those networks, but we considered individual layers. So we wanted to see what would happen when you classify based on the output of the first layer, second layer, all the way to the end. Okay? And we trained those networks, or those classifiers, to perform this animal and animal task that I showed you earlier. Okay? So if you do this, and you have enough, we worked with a big set of images, 100,000, you get as expected, a near linear trend. So what I'm showing you here on the x-axis is what we call the relative depths, because those layers, those networks have different number of layers. We wanted to put them all in the same plot, and so what we did is that we translated the individual layers into a relative index within the network. So what I mean by that is that an index of 0 corresponds to the input layer, an index of 1 is the topmost layer, irrespective of the total number of layers. Okay? And what you see here is a very clear, at least for all but one network, a very clear linear trend. The more layers, the better the accuracy. You start about 65% accuracy. Some of these networks, in particular a version of VGG 16 that we fine-tuned, all the way for animal and animal, reaches nearly perfect classification. In comparison, if you look at the level of accuracy of human observers on the same test images in a rapid speeded categorization task, we find a level of accuracy at about, I think this is 76 or 77% accuracy. Okay. Point being that, past a few layers of processing, those networks are already outperforming vastly what human observers can do in this speeded categorization task. All right. So, well, how can we compare the visual strategies used by those by the convolutional neural networks and humans? Well, so we tested human observers we run them on our test sets. So we considered a rapid categorization task very much in line with what I showed you earlier during this talk. There was a little bit of a novelty in that we use mechanical Turk, and it's not easy to control precisely timing on the order of millisecond on a hardware where you don't have control, including a browser. But we relied on the video player in HTML5. We can talk about it offline. We did a number of checks, and I think we can claim that we are accurate within 10 milliseconds. So I think I can look at people in the eyes and say, yes, we didn't have the same level of control as we would have had in the lab, but I'm pretty confident that the display was, on average, between 40 and 60 milliseconds. So because this is mechanical Turk, we were able to run a very large number of participants, nearly 300 participants, and over 2,000 images. So that gives us a set that's significant enough to have a meaningful comparisons with computers. So we got 2 scores over these 2,100 images. For human observers, we looked at the average number of observers that correctly classified this particular image, irrespective of the class label. So we know how difficult or easy a particular image is. And then for computational models, we computed, so a standard way to assess the confidence of a classifier is simply to measure the distance between the decision boundary and a particular image. Okay? And we normalize those scores, and then what I'm going to show you next are correlation between the score obtained for each one of the individual models versus our human score. And here it is. So for reference, this is what I showed you. This is accuracy. Here's a similar plot, but instead of plotting accuracy, we are measuring the Spearman correlation between humans and the models. Okay? And what you see here is a very different trend. what you see here is that there seems to be this inverted U-shaped curve, whereby the peak correlation between human observers and the models seems to be somewhere between kind of intermediate level of complexity. Okay. Notice that this is not just about accuracy, as in fact, if accuracy alone was able to predict this trend, we would have found a much lower number of layers for the peak correlation. So that's yeah.
Sorry, would you finish your thought and I'll ask my question?
No, go.
I just had a quick question about these. You said what you did was you took these models and then you took wherever you were in the chain and you added a 4K layer and you passed it into an SVM.
No. So we classify each layer individually. So this is the output of say conv1, conv2, conv3.
Did you? So you took
We don't
the output.
concatenate, so just the output.
I'm sorry, I didn't mean to say
Yeah.
concatenate. So you took the output and then you passed it into a 4K layer, fully connected, and then you did
No,
SVM.
so sorry, I want to be fast. So one of the issues is that the different network architectures would have different number of units in different layers.
Yeah.
So we wanted to, for instance, the lower layers can have hundreds of thousands of units, and so we wanted to account for that, and so we took random samples of units of 4096, which is the number of units, the smallest number of units in those networks.
All right, and then you passed it into a
SVM.
binary SVM?
Yeah,
or-
train on animal and animal with 100,000 images of animal and animal. Yeah, okay. So that's it. I mean, that's pretty much all I have to say about this plot. I think the trend is pretty clear. We find that the deeper network clearly outperform human observers, but they correlate less well than shallower architecture. And if you go back now from this kind of magic number, and what's interesting is that it seems to be almost independent of the total number of layers in this architecture. So there seems to be this kind of magical number. We're not fully sure what it is and what these deep neural networks are learning, but there seems to be this optimal peak correlation with human observers for relative depths of 0.7, 0.8. So the conclusion is that the deeper network today are able to achieve depths of processing, which is arguably deeper than what human observers can do during this rapid recognition tasks. So what is interesting, and I'm not going to show you in the interest of time, but of course, if you give human observers more time, both either presentation time or response time, you find that the accuracy increases. So when more time is available, people can increase their depths of processing in a sense. But we do not find that the correlation with deeper network actually improves. So what this suggests is that whatever it is that human observers are doing when more time is available is not well accounted for by deeper network where the depth is achieved through static layers that are stacked on top of one another. So I have my personal opinion, and I believe that what makes us different when more time is available is that the greater depth of processing is achieved through time. Particularly, we talked about some of these things over the human vision lunch, where I think ideas related to recurrent connections, integration of context, and some of these things play a key role, and those mechanisms are simply not taken into account into these computer vision systems. All right, so I'm gonna switch gear, so one point that I wanted to make here is that those networks are too deep. The other point that we believe was the other thing that we believe was going on is that we thought that possibly because of this backprop and all the biases that modern computer vision databases exhibit, we also think that something fishy is going on with the visual representations learned by those deep networks. Okay? And to study that and to convince you of that, we know how to probe the visual representations used by this deep network, or at least we have ideas. There's a lot of work being done, and I don't think there is a magic bullet at the moment, but we know about sensitivity analysis, relevance analysis. We know how to get a sense of how perturbating individual pixels affects the classification at the top, right? So with computer algorithms, it's not too hard to probe into the inner visual representations. With humans, it's not clear how you can do that. And so we came up with what we thought was far from ideal, but our best shot at it. And so we stole ideas from work by Louis van Haan that I think maybe some of you might be familiar with. I think the game was called Peekaboo, and the exact setup was different, but certainly that was a source of inspiration from us. So here's was our idea for probing into visual representations or object representations. So we considered a team of human players. So this is all from Mechanical Turk. We have a teacher and a student. The teacher is being shown in an image. The student starts from a blank screen. The teacher is told that it has the ability to click, that's what you see in blue here, on the part of the image that it wants. So there are constraints on how clicks can be done. But in general, to the first approximation, the teacher can click on the part of the image that it deems most relevant to recognize the object, and those parts that are being clicked become visible to the student. Okay? Now, the student has to figure out the correct category of the object as quickly as possible. The quicker the student figures out the category of the object, the more points they make, and all the teams compete, right? So there's an encouragement for not clicking at random, but making the most insightful clicks, in a sense. I can tell you more about it if you want in the Q&A, but we worry about a lot of things, and it's a little bit more complicated than that. It's not like people can just do salt and pepper. It's not like there's a constant constant speed, so people cannot cover too much of the image. But anyway, that's the basic idea. Okay. So if you get that, we get that for, and I should say that also the teacher and students alternate, and the teams switch regularly. So essentially you can get what we call a click map for an individual team and an individual object. So which correspond to all the pixels that were clicked before the student correctly recognized the category of the object. And then we can aggregate over multiple teams and then get a heat map that I will call an importance map, which correspond to essentially the most important clicks that were done by the teams before correct recognition was made. Okay. All right, so first again, I'm going to go quickly because I'm going to run out of time, but we did our homework, so I can tell you that we're not just measuring noise. The clicks we obtain within an experiment, across experiments for the same set of images are highly correlated. Again, I'm happy to, actually this is published, so you guys, or will be published by, in a workshop organized by Chris at ICCD on what's the name of the
mutual benefits of cognitive science, something like that.
All right, so I guess this is going to be at the end of the month, so after that, the paper is already available on our website. So we did our homework. We made sure that the measures were repeatable across trials and across experiments. So then the next question was, well, what is it that people are clicking after all, right? So after all, it's almost a weird task that we give them. So we wonder whether there was some correlation with saliency and eye movements. So we went to, there's a database of saliency maps, so where an eye tracker was used and saliency maps were derived. So we took part of the Silicon image database, so we had both the images and the saliency map. And so those are examples of images, example of maps we get, and this is essentially the corresponding saliency maps. And the correlation is not zero, but it's much less than the kind of repeatability we get when we run our Pictionary experiments. So part of it is saliency, but there is a lot more to be explained. All right. Now, we wanted to make sure that those clicks correspond to actual visual features that are useful for object categorization. We know that it's not saliency, but we still don't really know what it is. So we ran a control experiment where we assessed the usefulness of the clicks for visual recognition. Okay, so we ran a rapid categorization task, as we've done before. Here the task is to discriminate between dogs and vehicles. We wanted two classes of objects for reasons that will become clear. And then we only revealed part of the image, what we call the image revelation. So some percent of the click maps, starting from the most important click maps, and then going on. So you can have, for instance, 100% revelation for this image, which means that no subject had to reveal more than those n pixels, but that's still not the full image, just to be clear. Okay. And you see with a revelation of 1%, you cannot tell anything. With a revelation of 25%, you start seeing already visual features that give you very significant cues about the category of the object. Okay. And so here we ran two sets of stimuli. One set where the visibility of the features was controlled by the click maps derived from Pictionary, and another set where we did the same thing on the same exact images, but where the bubbles were what we call bubbles. So this image revelations were driven by saliency cues. Okay. And so what I'm going to show you next is the accuracy of people as a function of the amount of revelation on the x-axis. So the y-axis is % accuracy. Red is how the accuracy of people for the vehicle versus animal rapid categorization evolves. And you see that there is a very slow gradual increase from below chance when not everything, not nearly enough is visible, up to maybe a little bit more significant than chance. But contrast that with the blue curve, which is correspond to clicks that were driven by, which correspond to bubbles that were driven by the clicks obtained during click sharing. Okay, so there is a very significant difference. Clearly, the information that is associated, or the features associated with our click sharing game are, contain more information for object category than anything saliency related. All right, so our importance maps are repeatable, they are different from saliency, and they are useful for visual recognition. What I'm going to show you next is that they are completely different from the kind of information that deep neural networks care about. So here's an example, and I should say from the get-go that we try different methods for assessing those kinds of maps from deep networks. Here's the best results we could get. This is a sensitivity analysis. Once again, the idea is that you perturbate individual pixel intensities and then assess the effect on the top classification units. We tried LRP, we tried a number of state-of-the-art methods. The result is always the same. We get nearly zero correlation, and none of this is significant. And clearly, if you compare those maps to those maps, they look very different. The deep networks care, this is a glass frame. The deep network cares about the lens. People care about the frame. Tie, people care, or the deep network seems to care primarily about the shirt and the part which connects the shirt to the tie. People clearly care about the tie. So we're not fully, yeah.
Where people clicked, it was dark. In the heat map here, what's dark is more relevant, not
yes. So white means 0 and 1 means So it's going from white through shades of red all the way to black. Okay, so I'm tempted to conclude that the visual representations used by, and I should say this is a VGG 16 or 19, one of the two. And so it seems pretty clear that the information that those neural networks care about is somewhat distinct from what humans care about. Now, that doesn't mean that we have to throw away the entire architecture. One of the line of work that we are currently undergoing is literally to try to use this knowledge we are gathering from human subjects through those click maps to cue deep networks during training so that they start paying more attention to those features that humans deem important. And the basic idea, without getting too technical, is that when you optimize a deep learning architecture, you normally care about minimizing some kind of classification error. Here we're adding a term which is trying to simultaneously minimize the distance or the difference between the importance maps or the sensitivity maps derived from deep networks and the human case. Okay? And this is still ongoing. But one of the first hurdles we had to overcome is that when you have teams of human players playing against one another, it's really, really hard to go through a lot of images because you need to figure out ways to have people grouping them at the same time. There's never two people online at the same time, so you need to have a waiting room. And the number and the volume of images we're able to gather was not nearly enough for presumably the hundreds of thousands of images we will need to be able to properly train those networks. So we came up with a twist, and we came back with a second version of the game. So our idea was that essentially the hardest is to pair two humans, so we need to get rid of one of the humans. And so essentially the basic idea in this second version of the game is to replace, so I'm showing here a screenshot. You can actually, I don't know if the game is still on, you might have stopped it because it was starting to cost money. But you can check it out at clickme.ai. And so the basic idea in this second version of the game is to replace the student human by a deep network that's running on one of our servers. So essentially here we have humans, so that could be you starting on this game. You can choose where to place the bubbles on this screen. And then in the background you have a deep network, VGG 16, trying to recognize what's going on based on what's visible to the deep network. And then as soon as again, that's the same game, as soon as the network figures out, as soon as the correct category appears in the top 5, then the trial moves to the next one, and the human player gets points based on how fast the deep network recognized the image. Okay, so this way we were able to go from a few hundred click maps to about 500,000 click maps. And so what you see are examples of some of those click maps. So here you see images from the objects, and then here you see the associated click maps. So I wouldn't necessarily be able to verbalize what's going on in those click maps, but for several of them, the objects is actually almost recognizable. And so just a zoom-in version, I don't know if all that useful. All right, and again, we did our homework, we checked, this is a fairly different game, but we found that the correlation on the click maps, we used a subset of images that we tested in the second version, and again, we find that the correlation is significant and pretty robust. So the the deep network queued on the click maps is still running, but I just want to give you a flavor of what's happening at the moment. So here are example images, and here's what's happening for our two versions. So here's kind of red-pink is our relevance maps derived from an original kind of ImageNet pre-trained VGG16. And so you see that in general the information or the diagnostic information seems to be pretty distributed over these images. So it seems that there is a pretty broad visual strategy that cares almost about as much about the background as the foreground. What you see going towards blue is what's weighted more heavily by a network that has been queued on the click maps. And I should point out that those are test images, so the network was never trained on those images. And so you see that the blue now starts to appear much more along objects, and in particular maybe visual features that would seem important to recognize the dog. So here we see that there is a lot more activity around facial components of a dog face. Again, this is ongoing work. We're still training the network, but I'm pretty hopeful that we'll be able to have a visual architecture, a deep network that's going to behave much more like humans. Yes?
Very quick question.
Yeah.
Were all your samples black and white, or color, or both?
That's a good question. I believe everything is color, yes. Yeah.
Have you tried cross-training where you use the clicks on the eagle to train for automobiles?
So, no. So here we just train on so we don't necessarily distinguish. So, we sample, I think, uniformly from all the categories. So, there's 1,000 object categories and we have 500,000 maps. So at this point we have, about 500 images per category.
So this is after learning just where people click on all images, not
yeah, we didn't
specific to
break it down, but
dogs.
that's an interesting question.
okay.
So so of course those are left out images, but you're right. It's very, very likely that the network saw this particular object category before. That said, it probably never saw this particular image, objects in this particular configuration. So I would argue that finding the eyes and the facial features is still not trivial. But you have a point, and that would be interesting. Actually, you're right to leave out some categories and test how much the network generalizes to those left out categories. Again, this is very much I did this slide yesterday, this morning actually, because we skipped breakfast. Yes.
When a participant is playing the game, how long do they have before they have to make the first click? So
That's good. They decide when to start. That's a good point. So you can look at the image as much as you want, and then the first click starts the game, and then there is a drift that's being and then you essentially the position of the mouse controls the direction of the drift. But that's a constant drift to prevent people from either doing salt and pepper strategy or going really fast, and then that would be unfair to slower people. So we control the speed at which the image is revealed. The user can choose where to go and what features to emphasize. Okay. All right. How much time do I have, Chris? 10 minutes? No, less. I'm almost over time. Okay, so I need to. Okay, I'll try to make a brief last point in the 5 minutes that I have. So. I wanted to tell you a little bit about visual reasoning, and to make more explicit what I mean by visual reasoning, I'll ask you to a quiz. Look at the image 1 and 2 here on the left and right side of the screen, and can you tell me in which way those two images differ?
Image 1 is vertical, image 2 is horizontal.
That's interesting. That's a good point. Could have been. That's not the answer though. But I'm getting to that.
The left image has two identical objects, the right has.
All right, great. So you are smarter than a DCN. So most of what I wanted to show you next is that's the kind of stuff that DCN, deep convolutional neural network, cannot solve. Okay, so how can I demonstrate that? And we were convinced of it, but so in order to demonstrate that, we went back to a great paper actually by Fleury and colleagues from 2011, where they proposed a list of 23 problems which they deem synthetic visual reasoning tests. And so here are representative problems from this set. All of those are binary classifications. So you are shown positive and negative examples, and people have to come up with a sorting for the images. So here are examples. This would be an example. Red would be one class, blue would be the other class. So from only one positive, one negative examples, I think most people would be able to quickly figure out that the rule is across the surface here, and that's on the other side. 2 out of 4 objects are touching versus here that's 3. That's the same as before. Same up to a translation. I think there is something hidden here. I forgot. Oh, this must be. I think this is making contact on the surface underneath. They are all identical. At least one differ. A lot of those. There's an vertical axis of symmetry on those, not here, so on and so forth. 23 problems of this kind. And so we performed a systematic analysis where the challenge comes with a 1 million training image for each one of the 23 problems. We wanted to test the ability of deep convolutional neural network to solve those tasks, to learn to solve those tasks. And so we hyper-optimized the heck out of them. We optimized the depth of those network up to 8. We optimized the kernel size, the pooling size, so on and so forth. What I'm going to show you here is the accuracy of the best performing network architecture for each one of these 23 problems. And what you see here is the accuracy on the y-axis. Okay? So you see that there is pretty much a continuum. On the one hand, you have tasks that are very close to chance, even after 1 million training examples. And on the other extreme, you have tasks that are perfectly solved. So just to give you an idea, this is our first same different task here, which is just a little bit above chance. And this is an inside-outside task, which is perfectly solved with 1 million training examples. So what does this mean? Well, my student went back and tried to figure out what's special about the task on the left side and the task on the right side. And what they came up with was pretty striking to me. It turns out that pretty much all the tasks on the left that cannot easily be solved by a deep network are always judgments of similarity. So whether saying whether 2 shapes or 3 shapes or 4 shapes are all the same when one at least is different. Under certain transformations, so you can have translation, you can have 2D rotations, scale, and things of that sort. On the right side, what seems to be much easier are the spatial relations. Okay. The purple one here, which is kind of in between, turns out to be a blend. I forget exactly what it is, but this is, I remember that this was some kind of a blend between a decision that involves some spatial relation and some same different kind of mix. Yeah.
I just got to comment. I think because of the way the CNNs work, it gets more and more abstract as it goes. They aren't able to solve the stuff in the lab. If you had connections from the early on layers going to the fully connected layers, I think the CNNs would have done a much better job in this.
So we can talk about it. I would love to talk more about this. I don't think that will solve the problem because, so first of all, remember that those are toy tasks, right? Those are just the objects here are always just close contour. So there's no noise, no nothing. But the issue is that it's hard to conclude much from that. Primarily because we have no control over the variability. I'll get into I think there's something about the sample complexity which might partially tap into your question. But so we have no way to control the variability of the stimuli with this task. And in particular, all the tasks use different stimuli. So we wanted to have more control over that. And so I know that I'm running out of time, but my students came up with a simplified version of that, which they call the parametric synthetic visual reasoning test. The idea is very simple. We replace all of these beautiful closed contours by simple binary patterns. Now, if we do this, we can have the same different task where you just have to judge whether those 2 elements are the same or different, and then the same stimuli can also be used on a spatial relation task where the goal is to say whether they are more horizontal or more vertical. And of course, I'm showing you the extreme here, but there is anything in between. Okay. Also, because this is our own data set, we can control the variability of the stimuli because we can have patterns of different sizes. So thinking about rod memorization, which I think is what is going on, we can have tiny 1 pixel parameter patterns if we want, or we can have very large patterns, which would yield to an explosion in the number of templates you need to store if you were to just store templates. Similarly, we can control the spatial extent of these stimuli. So we can have the templates being very close to each other, or they can be very far apart. And again, if you were to memorize all the possible positions, presumably that could yield an explosion in the number of training examples needed. Okay, so just to make a long story short, 40 million training examples, and essentially we find that the spatial relationships, they can be learned perfectly, so these are like training curves, whether it's low or high variability. What's interesting is that for the same difference, you find a very different pattern. We find that either they can learn perfectly for low variability, they cannot be learned at all for high variability, and there is this very abrupt shift from 0 to everything for medium kind of variability. The point, and we should talk more, the point that I was going to answer is that what's obvious here about the fact that the network is just merely performing raw memorization is that even after we successfully train a network, if we change the parameter of the stimuli by a tiny bit, say we extend the spatial extent by 1 pixel, or we add 1 pixel to the pattern, performance collapses again completely and never recovers. So I think that has entirely to do with the fact that, and we are trying to formally demonstrate that, the way by which deep networks learn to solve this task is simply a template matching strategy, what I would call a shortcut. It's interesting because in terms of a shortcut, this seems to be a shortcut that's applicable and certainly related to a biological strategy. There is evidence for blob-like descriptors in higher visual areas, and that could be one of the ways by which we primates solve spatial relations. However, there is very clear neuroscience suggestive evidence that same different tasks require two things. They require working memory and attention, which are two of the things that these convolutional neural networks are lacking. So I think I'm over time, so I'll stop here. I'll finish with this word of wisdom. I think if there's one thing that we should all together work on is to focus on the mechanisms that are unique to primate vision, and I think some of those mechanisms include working memory and attention. And if we inject some of those mechanisms in deep neural networks, we'll be able to reach the next level in AI, which is, in my opinion, mimicking human visual intelligence. Thank you all.
Some people might have to leave, but I think we can take some questions. Yes?
It's fantastic talk. I have a mountain of questions regarding number 3, but I would like to go back to number 1, the first point you raised. You seem to make the claim that brains are able to make these decisions with fewer layers.
Yeah.
And
at least during speeded
yes.
rapid categorization.
Within that context, so that would argue that, in my mind, there's one of two problems. Either our networks don't need to be deeper, they need to be wider to be able to capture that representational power, or the nonlinearities that we are applying between these layers is not nearly as representative and captures nearly as much complexity that our brains are actually doing.
I would say the latter. Yeah, and I try to make this point. One way to increase the complexity, if you will, of the transfer function is via things like lateral connections, maybe attention, and mechanisms related to working memory, which would increase the nonlinear behavior of those units, right? And we know those happens in biological brains. We know that their contribution is limited during this rapid visual categorization, which is good news because potentially that allows us to tap in the coarsest base representation we can. But I think after that we need to worry about these processes because they cannot be ignored anymore.
I would agree that alongside a lot of these advances in the accuracy, we've seen that which gotten deeper. But we've also seen a change in the activation functions as time has gone on towards ReLU, leaky ReLU, delay.
Yeah. So just to be clear, I mean, more than just a transfer function. What I really mean is that when you look, if you treat a neuron, a biological neuron, embedded in a circuit, and you just treat, you try to approximate the transfer function, so the input-output of the neuron. It's orders of magnitude more complex than either a ReLU or hyperbolic tangent or whatever you want. So I think there's much more that needs to be captured. So it's not just static nonlinearity we need to think about, but what I call context-based linearities, which are going to be influenced by the context and other things.
Can I jump in? It seems to me the other part of that is the assumption that the brain has very few layers. Isn't that sort of based on our really grossly oversimplified model of V1, V2, V3?
It is, but the visual system is so fast, right? That's the problem. Is that when you stick an electrode in a monkey PFC, you find categorical signal within 120 milliseconds, and so 120 milliseconds, neurons cannot spike much more than 100 hertz, right? I mean, and that's pushing it. So that means at least a spike every 10 milliseconds. So you need at least a spike between neurons. So assuming the best case scenario, one spike every 10 milliseconds, that means 12 processing stages. I mean, that's it. That's the biological limit of the amount of spikes or information or processing stages that the visual system had to rely on to perform the computation. I know it's hard to, especially for someone working on attention, it's hard to digest, but that's the reality of it. At the same time, I think rapid categorization tasks are anything but natural. Right? So they come, there's no, we live in a more or less continuous world. We don't change our, the visual scene ahead of us. I mean, yes, we move our eyes, but there's a lot of continuity. We work with a lot of prior information and all these things, which we, specifically try to get rid of during this rapid categorization task. So, in a sense, we are really pushing the visual system to work, with the very bare minimum. So I would say if anything, it's a lower limit on what the visual system can do.
I think there's a question back there.
Yeah.
So early on in the talk, you mentioned that the feedback connections weren't believed to be playing a significant role in the fast categorization. I was wondering if did you consider the basal dendritic connections, the talk between neurons in the same layer, was that also considered not important?
Well, again, this is, so first of all, so you're right. I don't think anyone can fully roll out, say, lateral connections and things of that sort. But again, the critical piece here is that you get categorical signal within about 100 or so milliseconds. So compute it whichever way you want, 10 milliseconds per spike, you have not much more than 10, 12 connections or that you can make. So whether those connections, I agree. I mean, what we think of as feed-forward connections could be lateral, feedback connections, but you still don't have a lot. So I guess what I really meant was it's unlikely that you would have, just because of the sheer conduction delays, it's very unlikely that the signal would have enough time to go from lower visual areas onto higher visual areas, say IT, and then feeding back onto V1 and then going back onto, because you simply don't have enough time. Local recurrent connections, in fact, when you implement some of those networks, HMAX and others, when you worry about the biophysics, how to actually implement a max with neuron, when you look at the biophysical circuits, you actually need to implement things like normalization, and you end up with already a few recurrent and potentially both feed-forward and recurrent connections. So I'm not denying those. In fact, as I said, they are needed to implement the most basic operations in those networks. But what I mean is that it's very unlikely that you would have massive kind of top-down, the kind of models that people have been, the classical textbook psychology when once you've seen those ambiguous shapes, you can never unsee them anymore. This kind of feedback, at least active feedback, dynamic feedback, is unlikely to play a significant role at this time scale. That said, that's the other piece that I should be more careful when I make those statements. You're engaged in a task, right? So I know that some people here are working on attention. People are engaged in a task. So I'm not denying the fact that there might be some kind of priming happening in the visual system where I don't know what it is, but the visual system might be setting itself up to optimally detect animals. I'm not I cannot say anything about that. What I can say is that it's unlikely that massive say something like in a deep belief network or graphical model where messages will be passed from bottom to top and back and forth. That's unlikely to be at least what's driving those first rapid categorization. Yeah.
Actually, conveniently brings me to my question. Did the humans or the monkeys have practice time before they actually collect?
Yeah, so the monkeys are overtrained. They're overtrained, like they've been doing that forever. That said, when we compare to humans, we assess their accuracy on the very first presentation of a new stimulus set. So when I say the monkey reaches human level, they're actually 1.5% lower But that's on the very first presentation. I can guarantee you that after 5-10 trials, they already outperform humans.
Right.
For humans, we often start with a practice, yes, on separate set of images, again, just to make sure that they understand the rule.
Okay, so because one could argue that by controlling the time, the stimulus time, I mean, we can't really tell how deep we are actually going into the human. So I mean, it might be that when they are practicing, some connections or the weighting changes in the sense that they.
Oh, you're saying yeah. So let me see if I understand what you're saying. Essentially, which I agree. So we actually did the test. We varied the amount of time available for responses, and of course, there's a little bit of a delay in how people adjust, but they can adjust their response time.
Right.
So if I give you 500 milliseconds, you'll respond within 500 milliseconds, and you'll make a lot of mistakes. If I give you 1.5 second, you'll be able, after a while, to calibrate yourself to shift so it's never perfect, of course. But you're right, so what is it that they are doing? I don't know. I don't know if they are waiting longer to make that decision at the, decision level, category level, or if they are doing something else, adding more, I don't know, you're right. And you're right in the sense that we can make back of the envelope calculation. I could tell you, it takes about 50 milliseconds, to go from, V1 to V4, for instance, or 40 milliseconds. And so if I time an eraser mask the right amount, I can make sure that, the feedback hits the mask and it's useless. But, these are pretty big, nobody really understands fully, what's going on, and so it's always hard to tell. But one piece of evidence that I could tell you is a study we published last year. What we find is that there is an actual very strong correlation between, so we perform a decoding study on neural recordings along the ventral stream in those monkeys. And we try to decode for every time point, using a standard classifier, whether an animal or not is presented. Okay. So you start, at about chance. We find that already in the monkey, at about 80 milliseconds, you can already start to decode on some trials. Some trials take a little bit longer. But what happens is that if we now sort out the trials according to the reaction time, right? So we bin them into quartiles from the slowest to the from the fastest to the slowest reaction time. We find that the decoding actually follows. In other words, on those trials where the monkey is the fastest, we decode the categorical signal earlier from the ventral stream. When they get slower, we decode slower. So I don't know what it is that they are doing, and I guess I don't know how much that answers your question. But what I can say is that there seems to be a link between the latency of categorical information available in ventral stream, as measured by the decoding, and reaction time. So I don't know I don't know what direction it goes. I don't know whether, it's possible that most likely to be that on easier images, you can decode faster, and then the monkey makes a faster decision. But it could go the other way around, right? That somehow the monkey has a way, there's something called the speed accuracy trade-off, and the monkey might be able to, adjust its reaction time, and that in turn that affects the processing, time available at different stages of the processing.
Well, let's thank our speaker one more time. There's coffee and cookies out there.